In this video, we're going to talk about three-dimensional coordinates. So this is very important because the world we live in is three-dimensional space, right? So we're going to want to know how to work with these if we're going to talk about physics and engineering and things like that. And what we're going to do in this video is we're going to start by looking at just reminding ourselves of how two-dimensional coordinates work, and then we're going to see how those things extend into the three-dimensional realm. All right? So let's go ahead and take a look. Here we have a two-dimensional coordinate system. So just to remind you of some of the things we talk about when we have two-dimensional coordinates, we have our x-axis going horizontally here and our y-axis going vertically. Okay, and this splits the plane, that is the flat surface that is coordinatized by these axes, the xy plane. It splits it into 4 different parts. Over here, up here, we have the first quadrant, quadrant number 1. Here we have quadrant 2. Here we have quadrant 3. And here we have quadrant 4. So sometimes you'll hear people talk about the quadrants to just kind of give you an idea of where things are located. And we talked in some previous videos about vectors. All right, so let me plot a vector here. And I put this vector in standard position because you always can put vectors in standard position. And you can see we have vectors that we can draw in our two-dimensional coordinates. And the way we specify the components of these vectors, in this case the components are 2 and 3, the way we do that is just by, if we put the vector in standard position, all we have to do is extend a line downwards until we hit the x-axis, and that's our x component, the 2, and extend a line horizontally until we hit the y-axis, and that gives us our y component, which in this case is 3. Right? So that's how we can determine the components of a vector. All right. Some other things that we might want to do in 2 dimensions is describe the equations of lines. All right. So you've heard about y equals mx plus b and stuff. Let's start with something very simple. We'll just look at what if I just take an equation like x equals 2. Well, you can see what just happened here. I got this line over here. It's a vertical line. Why is that? Well, it's describing the set of points, all of whose x coordinates are 2. So every point on this line has x coordinate 2. And that's what this equation is demanding, demanding that x equals 2. I'm not demanding anything about y. Y is not in that equation. Y can be anything. And so we get a vertical line. Y doesn't, all that matters is that x is 2. Y can be anything. So all these points whose x coordinate is 2 form a vertical line. If I said x is -1, you can see we get a vertical line over there at -1. Now what if I do y? Y equals -1. Well, now we get a horizontal line because now we're describing all points whose y coordinate is -1. Right? But the x can be anything, so that means that line can go horizontally anywhere, right? But the y coordinate has to be fixed at -1. If we say y is equal to 3, we get this horizontal line up here, right? So horizontal and vertical lines. The reason I'm pointing these out is because we're going to talk about something analogous in 3 dimensions, which will be quite useful for us. Next thing that you might learn about in two-dimensional coordinates is how to compute distances. All right, so for this, I'm going to just use a piece of paper here. So if I want to compute the distance between 2 points, so suppose I have a point over here and I have a point over here. Okay, and suppose that these points have coordinates. All right, so this is my first point, so its coordinates are going to be x1 and y1. All right, so x1, y1. And this is my second point, so I'm going to label its coordinates x2, y2. And the question here is, how do I measure the distance between these 2 points? In other words, I want the length of this straight line segment that joins them. And we're going to call that distance d. So what is it? How do we find it? Well, play around a little bit, use your knowledge of geometry, and probably one of the things you'll try is to make a right triangle here, right? And if we can find the lengths of the legs of this right triangle, let's do that. Well, let's see. This leg goes from x1 to x2, and so therefore its length is x2 minus x1. This leg goes from y1 to y2, and so its length is y2 minus y1. And since now we know the lengths of these legs of the triangle, we know how to find the hypotenuse, right? We use the Pythagorean theorem. So from the Pythagorean theorem, we know that the distance is the square root of the sum of the squares of these, right? So we're going to have and there we go. The distance formula for the distance between any 2 points. Very important formula to remember. What can this allow us to do? Well, what if we start talking about circles? Okay, if I come back to my coordinate system over here, let's get rid of this stuff. Let's plop down a circle. I'm going to put my center anywhere. Let's put my center there. And then I'll specify the size of the circle by plotting some other point somewhere. Okay, so let's put it over here. So there it is. I got my circle. What defines this circle? Well, a circle is a set of points, right? It's the set of all these points that go around here. What do they all have in common? Well, they are all the same distance to the middle point B that this point C is. Okay? So all I need to do to define all these points is specify what that distance is. And then I'll just say, well, the circle is the set of all points who have that distance. So we just talked about the distance formula. So let's use that to find an equation for this circle. Okay, so our circle, let's say the center point, let's call that P. I think I may have called it something else in the picture, but let's call it P here. And then Q, let's let that be our other point. Okay, so P has coordinates. Let's call them A and B. The x coordinate is A, the y coordinate is B. And Q has coordinates, let's just call them X and Y. The circle is going to be the set of points that form this curve, which, as we said, was the set of points that are equidistant from P. So what we need to do here is we need to find the distance. And that distance, we called it D before, but since this is a circle, we know we call that the radius, so I'm going to call it R. So to find an equation for the circle, what I'll try to do is find an equation for R. Well, the distance formula that we just talked about said that the distance involved the difference of the x coordinates and the difference of the y coordinates, right? So if I want to write down an equation for R, the distance squared, the square of the radius, if we just use what we learned before, I'm going to take the difference of the x coordinates squared plus the difference between the y coordinates squared. And this is just the distance formula. But lo and behold, look what we have. We have an equation for a circle. A and B are the center point. That's the coordinates of the center point. And R is the radius. So if we know the center point of a circle and we know its radius, this is how we write down the equation of a circle. Okay. Hopefully that was mostly review for you. Maybe you forgot a few things, but now we're all up to speed. So what we're going to do now is we're going to go to 3 dimensions and talk about these things and what's going to happen in 3-dimensional space. Okay, so here we go. Here I've got, let me turn these colors off for just a second. Okay, so here we have the 3-dimensional coordinate system. So not only do we have an x-axis and a y-axis, but we also have a z-axis. And notice that all these are perpendicular to one another. Now, the way this is oriented, and the way we usually orient it, is so that the z-axis is the one that's pointing up. So unlike before, the y-axis was pointing up, now the z-axis is pointing up. The x-axis is the red one here, coming out this way, and the y-axis is the green one, going this way. And so we can orient ourselves in different ways. There's no one way to orient this thing, except we usually, like I said, have the z-axis pointing up. But otherwise, it's a little bit more of a, you have a little bit more freedom in how you decide to lay this thing out. Okay. In two dimensions, we split the plane into quadrants. Well, here this is splitting the three-dimensional space into octants. Octa meaning 8. There's 8 of them. If I plot this plane here, this is a flat surface that is perpendicular to the y-axis. This is called the xz plane. This is the xz plane. It's perpendicular to the y-axis. And if I look at the plane that's perpendicular to the x-axis and goes through the origin, that is called the yz plane. It's perpendicular to the x-axis, the yz plane. And if I take the plane that's perpendicular to the z-axis and goes through the center, that's called the xy plane. And you can see that this does indeed split three-dimensional space into 8 regions. Above the xy plane, we have 1, 2, 3, 4 up here, and then we have 4 regions below the xy plane, right? And so we actually have split three-dimensional space into 8 regions, and these are called octants, right? There is a numbering, there are ways to number these, but I don't think we're going to have to be so particular that we need to remember the numbering, but know that this happens. Okay, so what about vectors in 3 dimensions? Okay, let's take a look at that. Okay, so here we have the three-dimensional coordinate system, and I've got a vector plotted. Notice I can move this vector around. Now, it's not very easy to see exactly where this vector is, all right, unless I really start rotating the view around. But one of the things that I've done to help identify where that vector is I've drawn these line segments. So if I turn them off, all right, you'll see that it's even harder to see. Where is that pointing? Is it pointing? Is that positive z or negative z on that vector? If I move it up or down, I might get some idea, yeah, okay, I can kind of see it's z is positive, now it's negative. But it helps to to extend a line, a dashed line below the vector down. Oops, that's not the right one. Which line is that? That one. So I just drop a line down to the xy plane, and then I'll drop a line over to the x-axis, and then I'll drop a line over to the y-axis. And that kind of helps us get a picture of where this vector is, because without those lines, those dashed lines as a frame of reference, it's really hard to see without being able to spin this thing around. Okay, and so that is a good way to kind of describe where your vector is pointing, and a good way to plot your vector. All right. Let me make this vector. Let's give it nice coordinates here. Let's see if I can do that. Okay, there's the vector. See, in this picture, if I didn't have those lines, it looks like it's on the y-axis, but of course it's not. If we spin it around, we can see it's not, and that's why those dashed lines are helpful. Now, one thing that you're going to want to be able to do is graph these things not using an app, because you may be at a whiteboard talking to somebody else and you need to quickly describe something in 3D. You may not have a computer to do this, and you may not want to type all this stuff in to get it to work. So how are we going to do this by hand? Well, what you're going to do is you're going to draw your axes, right? So remember we said the z-axis points up. All right. Now, you're probably tempted to draw the x-axis pointing this way, but don't. Usually you put the y-axis pointing this way. The x-axis, you want to think of it as coming out of the page, coming out at you. To draw that, the technique for drawing to simulate the idea that something's out, you draw it coming out is to draw it at a diagonal. So the x-axis is pointing this way. And this is usually how you'll see people draw three dimensions. Now let's plot that vector 3, 4, 2. All right. Oops, I'm going to be in the way here. Right here. Okay. The vector I'm going to draw is the vector 3, 4, 2. Okay. And let's just see how we do that here. Well, first I want to tick off values on these axes as evenly spaced as I can. I don't know that I did a great job there, but 1, 2, 3, 4. Okay, so notice the direction, the extent in the x direction is 3. So I'm going to go 1, 2, 3. Okay, and then the extent in the y direction is 4. So now I'm going to step out 4 spaces. So I'm going to go 1, 2, 3, 4. Maybe an easier way to do that is actually go 4 spaces in the y. You know, mark that. I went 3 in the x. And then I'm going to extend a line parallel to the y-axis coming off the x. And then I'm going to extend a line parallel to the x-axis coming off the y-axis. Right? And that gets me right here. So this is where the vector is in the xy plane. Right? But we know that its z-coordinate is actually 2. So I'm actually going to have to go up 2 here. So I could measure that and go up 2 here. It looks like I'm going to be right here. Right? The other thing you could do is you can continue to draw these dashed lines parallel to the axes until you make a box. And the vector will point to the corner of the box. And it will start here and come out that way. Right? So that's how I would draw my vector. And by drawing that box, I'm giving the viewer a better idea of where that thing is actually pointing. Okay, so this is how we draw in 3 dimensions, the 3-dimensional coordinate system. Okay, what are some other things we talked about? We talked about distance. Well, how does distance work if I take 2 points in space up here? Suppose this is point 1, so it has coordinates x1, y1, z1, and this is point 2, so it has coordinates x2, y2, z2. How do I define the distance between these 2 points? Well, there's a nice formula for it. Here it is. The distance between 2 points in 3-dimensional space. Notice it's very similar to the equation that we had for 2 dimensions, which look like this, but we just added a z part. Right? Now, one really good exercise for you is to prove why, explain why this is the formula for 3 dimensions. It's not terribly hard, but it requires a little bit of thought. It's not obvious. I don't think it's immediately obvious. I think it makes sense that all you'd have to do is add a z part. I mean, it's nice, but I don't think it's immediately obvious that that's exactly what's going to work. But with a little bit of thought, you can see that why this would actually be true. Okay, so one thing I want to go back to and look at is the idea of equations of planes. All right, so I'm going to write x equals... Actually, before I do this, think about what I'm going to get. I'm going to write x equals 3. Imagine what shape I'm going to get if I graph that. X equals 3. All right, you got it? Let's see what we get here. Look at this. I get a flat surface passing through x equals 3. Well, that makes sense, right? Well, that's okay. But look at the surface. It is a flat plane. It's parallel to the YZ plane. Why is that? Well, what we're looking at is we're looking at the set of points whose x coordinates are 3. But the y and z coordinates can be anything. But the only thing that needs to be fixed is that the x coordinate is 3. And so if you imagine what that gives you, it's exactly this. The y and z can be anything, but x is 3, so it's just going to be parallel to the yz plane here. What happens if I do y equals 3? Well, here we are. We get something parallel to the xz plane. We get the set of points whose y-coordinate is equal to 3. And we get this plane. Okay. What if I do z equals 3? What am I going to get? By now you probably have the hang of this. I'm going to get the plane that goes through the z-axis at 3, and it's parallel to the xy plane. See, the x and y coordinates could be anything. They're not specified by this equation. The only thing that is specified is that the z-coordinate is 3. So we're seeing all the points whose z-coordinate is 3. So we can describe some simple planes this way. Z equals -2, for instance, would be the plane that's down there. All right. So those are some kind of just basic planes. Of course, there are other planes that go at diagonals and things, but we'll talk about those in a different video. And then what's the analogy to a circle in 3 dimensions? It's a sphere. So how do we define a sphere? Will it let me plot a sphere in here? Sure will. Okay, so I plot the center point, and then it wants a radius, right? So it wants another point that's on the surface of the sphere. And when I do that, couldn't even tell where that was until I started rotating this around. I can see my sphere, right? So you'll notice I got a point in the center over here, and then I got a point on the surface of the sphere, right? So how are we going to describe the equation for that? Well, it's really pretty much the same picture when we draw this out. I got my point in the center, let's call it P. I got my point on the edge of the sphere, let's call it Q. Now our points now have 3 coordinates. So my center point will have an x, y, and z coordinate, A, B, and C. My point on the edge will be x, y, and z. Okay. And what defines a sphere? Well, it's the set of points that are this distance away from P, the same distance that Q is. So I just have to find this distance. We're going to call that r for the radius. Can we write down an equation for r? Well, I think we definitely can. If we go back to here and look at the equation for the distance between 2 points, here it is. If I square both sides, I've got my formula for the radius squared, right? So it's just the difference of the x squared, difference of the y squared, and the difference of the z coordinates squared. So let's go ahead and do that. The square of the radius is going to be the difference of the x, so x minus a squared, difference of the y, and the difference of the z. Each of those squared added up. This is the formula for a sphere centered at ABC of radius r. Okay, and that's where we're going to end this video. So just working a little bit in 3 dimensions.